But let me give a little introduction, if you'll allow me.
Yeah, sure. Yeah, sure.
Um, so no, you don't have to go over there. The uh, with the sea ice modeling, I've been doing this a while, and the ice model hasn't actually changed all that much in terms of physics in a very long time. We've been kind of tweaking it, add melt ponds, do things like that. Nicole's done a ton of work getting the VTC to work, which is great. But in terms of the sort of the physical underlying sea ice model, there hasn't been that much change. The latest big thing that happened was the flow size distribution. And so that's what we're now bringing into E3SM so that we can work with the waves and all that. So that's really cool. The flow size distribution is kind of a fundamental change because the basic variable description in the ice model is an ice thickness distribution. And now we're adding flow size as basically an argument in that. So it's an ice thickness and flow size distribution as a single variable. And it's all interactive. Okay, so that's kind of a fundamental change in the sea ice model structure and the physics and what you're doing. What Andrew's doing is even more fundamental than that. I really think that this development work that he started at NPS and has continued for a while, we're finally at the point where we can get into the model, is like the greatest thing to happen to sea ice modeling in the last 30 or 40 years. I'm serious. It is a fundamental error in the model right now that we're about to fix. And so I'm like, go Andrew.
Golly, I don't know where to go after that introduction. So since you don't have any slides to look at, this is a virtual poster, and I've got a QR code you can scan and bring up the virtual poster that you'll see tonight. But it's actually better that I talk to this issue. So, in nearly as long as basin scale sea ice models have existed, sea ice mass has been approximated with the sea ice thickness distribution, so a probability distribution of different thicknesses within the pack. So why do we do that? Why don't we just have a single thickness of sea ice? And the reason is that, first of all, thermodynamics are strongly nonlinear. So growth is strongly nonlinear with thickness. So very thin ice grows really rapidly, and very thick ice just grows incredibly slowly. So we have to represent that. And the other reason is that only a very, very small portion of the pack can be really thin ice, and that can dramatically change the compressive strength of the pack. It can become incredibly weak with only 1% or less of thin ice, and the rest could be 5-meter thick ice, and it doesn't matter. And so we had to represent it with this thickness distribution. But the problem with that is that it's always been debated whether that really is an appropriate descriptor of sea ice morphology. Sea ice is a heterogeneous material. It has lots of jagged edges, and it isn't just this nice distribution of thicknesses. We can get that with observations, but there's a lot more going on in the pack. So Drew Rothrock, who originally devised the thickness distribution, actually wrote a paper on this about 20 years ago saying he doesn't really think this is an appropriate descriptor of sea ice. But no one really knew what to do. So about 7 years ago now, Elizabeth and I were trying to fix some new physics in the model, form drag, and they needed a representation of a sea ice ridge in this, and we found that under certain circumstances the solution was ill-posed. And so we were trying to fix this, and in the process of just coming up with some very basic fundamental pictures of sea ice ridges, we just made a polygon, and we added porosity. We realized that if we observed all of the basic equation of sea ice floating, the whole size of the ridge expanded out dramatically, the depth expanded out dramatically. So in other words, if you're sending out a depth, you're increasing the thickness of the ice, but you're not adding any more mass. And so for as long as we've been modeling sea ice, we've been representing mass with this thickness distribution, but that's very dependent on the macro porosity, and ridges have up to 30% of just open spaces inside them. And so this is really fundamental because it means we're getting our mass wrong. in ridges, and the way we represent jagged edges and the topography of sea ice is just wrong. So we published a paper in 2019 showing this and showing how you can incorporate this macro porosity of sea ice. It was quite a long paper. In fact, the reviewers said we should split it in two, and we didn't want to do that. So we published this really long paper, and there was one thing left hanging. We did all of our experiments assuming pure compression of the pack, but in reality, there's flows and they glide past each other. There's lots of shear, and we weren't really quite sure what to do with that. And so two things happened after that. I had a master's student at NPS who, for a start, we weren't sure whether our analytic solutions were quite correct, and he built a discrete element model of a ridge with Adrian Turner's help, and his solution just the equilibrium state landed right onto the valves, which is encouraging. And then we were able to compare it with some submarine data, first of all with about 700 ridges, and we got some quite good agreement. But then fell out of the sky. I got an email from Andrew Mahoney at University of Alaska a few years ago saying we have 64,000 ridges with which you could compare your model. Are you interested in being on a GRL paper? And so up until that point, the biggest data set that's ever existed is 700 ridges. This is it's dramatically increased, 64,000 ridges sensed in various places in the Chukchi and Beaufort Seas, and it was a shell data set. So oil companies do have their uses, and we were able to determine, first of all, that our model worked really well compared to the ridges, but we were also able to work out how to represent shear, and that in fact, because those flows are all bobbing around together, they're all shearing against each other at the subgrid scale level, down at the 10-meter level, and so we don't even need to worry about shear. We just apply an isotropic approximation of shear. So the shape of ridges, the average shape in a grid cell, which everyone's been getting wrong, and on which currently the way we build ridges in a sea ice model is not this nice triangular shape. It's a cusp shape like this, and that's because of shear. So individual ridges aren't shaped like that. They are kind of triangular, but when you average them all out, they've got this nice cusp shape. And we worked out that the average macro porosity, when you include that, is around about 15 to 20%. So that means that in deformed ice, which can be a large percentage of the pack, we're getting our mass wrong by 15 to 20%, which is a lot. And I suspect this is one of the reasons why we don't get, for example, the timing right of sea ice gain or loss in the Antarctic. I suspect it's the reason why sea ice is decaying much faster in the Arctic than models have been able to do, because we've actually got too much mass in our models. And so there's a poster you can come and talk to me about this afternoon, and that's all I have to say. Thank you. Question? Yes, Nicole. Okay, so I've so far just talked about the dynamics of ridging, and you're talking about the thermodynamics of ridging. And at the moment, I'm toying and I'm playing around with how we do this with mushy layer thermodynamics. And there is a boundary term we could potentially use for mushy layer, but it's not. I don't think that's going to work very well, and I'm sure Adrian thinks that's not going to work very well. You're the mushy expert in the room, so yeah.
Well, I think one of the important physical processes that we're not doing right in the model right now that's associated with this is that the weight of the ridges tend to pull down the ice flows so that they kind of slope into the ridges. you know? And then especially in the Southern Ocean, in the Antarctic, there's liquid water all along the outside of the ridges and probably inside them too. Because that, water comes up from the seawater and then pools around those ridges. And that's where a lot of the biology was in the Antarctic, or is, maybe I should say. And so I think we have a chance of getting at that by combining your ridging and macroporosity scheme with your brine parameterization that's in the model right now. Yeah. 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 I think we need to get the basic density of the ridges first, but then figure out what that does to the hydrology. Gisela.
Okay. Yes. So
Repeat the question.
So the question was, uh, can I comment on how this could affect surface drag? So one of the things we have in the sea ice model right now that isn't switched on is form drag. So we divide up the edges that flows, the impact of ridges and skin drag, and the impact of smooth ice or smooth surfaces associated with melt ponds. And you can sum all that up to come up with a drag coefficient for sea ice rather than just applying a bulk number, which is what we're doing in E3SM at the moment. But to do that, you need a sub-grid scale representation of roughness. And so we can actually calculate a Z0 number, surface roughness, from using this method because we're basically building up spectrums of ridges, just like modern cloud schemes build up shapes or distributions of cloud within a grid cell. That's kind of what we're doing with the ridges, building up whole spectrums of ridges. So we have a roughness that we can approximate. And it's scaling too, which is kind of interesting, which agrees with observations. So it's a complex surface. Oh, okay. So, all right. Are you the person I talked with on Slack? Okay. So that we don't know yet because we need to have it in a basin scale model to work out. So what it does is change the compressive strength of the ice, and that's a hugely influential. I mean, that determines lots of things, where flows fracture and that sort of thing. Okay, so then the question is, up till now, what we've had is a column scale model. We've been able to compare it with 3 different sets of observations. It's actually been independently compared with ICESat-2, the end results, in a recent GRL paper, and they found that what we predicted came out exactly right in ICESat-2. So we're really confident this is going to work. But then on top of that, now what we're going to do how do we understand whether it works in a big model? And the way is to do it with an orbital evaluation. So from this, we can calculate freeboard. We know exactly what our density of our ice is, and it's varying this time. And ICESat-2, CryoSat-2 all fly over and measure freeboard of the ice. So separately, I've developed some algorithms to fly through the model and sense and build statistics of ridges and ridged ice and level ice, and then compare that with what the model produces. So this is the closest you can get to really understanding how well the model reproduces mass. And it's nice because these sensors that sense sea ice freeboard are on the scale of sort of 5 to 14 meters, which is way below our grid scale. So we can truly, there's no scale issue, which there is, say, with SSMI data. It's like, well, E3SM is already simulating below the scale of passive microwave data. So is the model right or the observations right? Whereas in this circumstance, we completely know that we're well below the scale of the model grid cells. Yeah, Nicole.
The flow size distribution, I intend to have it so that it's available in V3. It probably won't be turned on because there will be quite a lot of more testing to do before it's actually turned on, but it should be available for testing in V3. Otherwise, I think most of the parameterizations that will be turned on are exactly the same as they are in Impasse the Ice now. You know, that standard configuration. And then, of course, the BGC, which is, yeah, it should be the same. And so that should be available. And what am I forgetting? Isotopes, that's another new thing that's coming in with IcePack that E3SM wants. And so that will be, again, available but turned off. It may not be fully implemented, actually, because that requires coupling stuff. Right, right. Yeah, my target is to get the ice pack version of Impasse Sea Ice working the same as it is currently with the same options that you all use. And then the flow size distribution because we need it.
And from an ocean perspective, having that available is the flow size distribution is a really useful thing to know how much that's impacting the ice edge in the North Atlantic.
Yeah. They're still working on it. Yeah, the coupling with WaveWatch 3 is pretty challenging, I think. And, you know, just because there are feedbacks between the waves and the sea ice. And I think right now it's all going one direction and the way the ice is breaking up too much, I think. That's what I'm remembering. And so they don't, yeah. And so
tiny.
yeah. Yeah. And so they're still working on that tuning at this point. It affects the lateral melt rates. Yeah.
And the albedo of the
I'm not sure it affects albedo.
indirectly.
Well, indirectly.
Yeah.
Well, yeah, well, everything affects albedo indirectly.
Yeah.
Vslav. I have to think about this.
No, but the marginal ice zone is becoming increasingly in the
Yes.
central Arctic. So that's what used to be good, solid, wholehearted ice is now marginal ice zone. We're at the time.
Okay.
Time.
All right. Any last comments?
The place is literally falling apart.
Okay. Thank you all. And thank you to everybody online for joining us. Sorry for the late start. I think we managed to recover. So we'll talk to you all later. Thank you.